Hi, welcome to AB Video 1.4D Part 1, Continuity on an Interval.
They're going to give you a function and they're going to give you the graph. As it turns out, we're really going to be using just the graph at this point. All it's going to say is discuss the continuity of each of the given functions. Better directions, and the directions that I will be asking, are A, at which values is the function discontinuous? And you'll simply observe that from the graph. So anywhere there's a break in the graph, remember we talked about the three kinds: point discontinuity, which is a hole, infinite discontinuity, which is a vertical asymptote, or jump discontinuity, which usually happens with a piece function. Then you're going to be asked to justify. Remember we talked about the trilogy for f of x to be continuous at x equals c. F of c has to equal the limit as x approaches c from the left of f of x has to equal the limit as x approaches c from the right of f of x. So here's number 28. They give you the function, they give you the graph, but really we're going to be concentrating on the graph itself. So the first question is, at which values of x is the function discontinuous? So you can see the only place where you'd have to lift your pencil off the paper is at the point discontinuity, so it's discontinuous at x equals -1. So now you're asked to justify why it is not continuous at x equals -1. Well, if it was continuous at x equals -1, then the trilogy would work with -1. So basically, I'm sorry, this is leaning. I must have been having a bad day that day. You're asking yourself, is f of -1 equal to the limit as x approaches -1 from the left of f of x equal to the limit as x approaches -1 from the right of f of x? And you'll notice over here I've said that this is going to earn the majority of the points. I need to see this exact statement because that's the formal definition of why a function would or would not be continuous at a number, -1. So, as it turns out, of course, f of -1 does not exist. There is no point at all here where x equals -1. The limit as x approaches -1 from the left and from the right as well is this height of -2. And I don't know why I wrote -3. Isn't that interesting? So, let's just change that out. And let's say -2. And -2. Now, I know you're going to want to stop and say, oh, why can't I just say, well, in that one part doesn't exist, the very first part, f of -1, can't I just stop? And you'll see later why you cannot just stop, okay? The reason is going to be because of what we call one-sided continuity. So you do need to write all three, you do need to give me the values of all three, and of course, because of the does not equal, that is why it is discontinuous there. Okay, so same idea, number 30. Again, they're giving you the function. Who cares? Right now, we're going to be doing it all very graphically. So, as you can tell, there's one spot where you'd have to lift your pencil off the paper, and that would be at x equals 1. So it's discontinuous at x equals 1. In order to justify that, you'd be asking yourself, is f of 1 equal to the limit as x approaches 1 from the left, etc.? And you have to find the values of all three. Now, in this case, f of 1 actually does exist. It is 2, because there's a point right here. But the limits as x approaches 1 from the left and from the right approach a height of 1. So you're basically saying, is 2 equal to 1 equal to 1? Well, of course, this is not equal, and that's why it's not continuous there. Okay, we're now moving on. What we've been doing so far is a function continuous at a number, whereas now we're going to be talking about a function continuous on an interval. And we're going to start with what's called an open interval, which is round parentheses on both sides. In other words, non-inclusive, does not include a or b. And basically, a function is continuous on an open interval from a to b if it is continuous at, like we have up here, all x values between a and b. Now, obviously, you can't check and assure that it's true for all real numbers between 2 and 7, because that's an infinite number of numbers. So, for example, if you're told that f is continuous on the interval from 2 to 7, then that would mean it would be continuous at all x values between 2 and 7. So it could, like, not that this would happen because this would be too easy, but a multiple choice question would say that this is true, and then say, therefore, is it continuous at 5? Yes, because 5 is between 2 and 7. Is it continuous at 4? Is it continuous at 6? Yes, yes. Is it continuous at 7? No. because of the round parentheses. Is it continuous at 9? No, because 9 is not between 2 and 7. Okay, now we're going to talk about continuity on a closed interval with square brackets at both ends. Okay, now this is interesting. A function is continuous on a closed interval from a to b if it's continuous on the open interval, meaning it's continuous everywhere between a and b, and it's continuous from the from the right at a, it's continuous from the right at x equals a, and it's continuous from the left at x equals b. I know that sounds confusing, but what's happening is it is continuous not at a, because to be continuous at a, the limit as x approaches a from the left would have to equal the limit as x approaches a from the right, and we're not looking at anything to the left of a. But the square bracket implies basically that the limit as x approaches a from the right actually will equal f of a. There'll be a filled in dot at the place where your limit is approaching a from the right. Similarly, this square bracket around this b means that f of b will equal the limit as x approaches b from the left, and we call that continuous from the left. A picture's worth 1,000 words. Here's an example. So you can see in this example it's certainly continuous everywhere between 2 and 6, but then we have a filled in dot here and an empty dot here. Well, in this case, the limit as x approaches 2 from the right is equal to 1, but f of 2 is also equal to 1. So that's going to allow us to put a square bracket around the 2, because it is continuous from the right at 2. F of 2 equals the limit as x approaches 2 from the right. However, f of 6 doesn't exist, so the limit as x approaches 6 from the left of f of x, which is 4, does not equal f of 6, which just does not exist. And that's why there's a parentheses there. This type of interval is either called a half open or half closed interval, depending on whether you're an optimist or a pessimist, and you see the glass is half full or half empty. Okay, so as I said, this implies f is continuous on the open interval, continuous from the right at 2, and from the left at 6. Now, f is not continuous at 2, so you can't imply from this that the square bracket means it's continuous at 2. It's not continuous at 2, because the limit as x approaches 2 from the left doesn't exist. There are no points there. The largest interval on which this function is continuous is that square bracket 2 to round parentheses 6. So here's another example. As you can see, it's continuous everywhere between x equals negative 2 and x equals 5. There's no breaks in the graph. But here you have an open dot at the negative 2, a closed in dot at 5. So it's pretty easy. If there's an open dot, you'll put a round parentheses for the continuity interval. Filled in dot, you'll put in a square bracket. Okay? Again, I want to emphasize this does not imply that the function is continuous at 5. It does imply that it's continuous from the left at 5, meaning that the limit as x approaches 5 from the left of x does indeed equal f of 5. Okay? All right, so here's one thing that's very important for you to realize. Sometimes the interval of continuity will be the same as the interval of the domain. Let me just draw you a quick graph for that on my nifty screen. For example, if I had a pure polynomial function, okay, what would happen in this case is the domain of this function, as you can see, would be all real numbers, right? But the largest interval on which it is continuous is also all real numbers because there's no breaks in the graph. However, in this particular case, the domain is all real numbers. There are all the numbers to the left of negative 5. We do have a point that's called negative 5 something, everything between negative 5 and negative 1. We do have a point, etc. So the domain is actually all real numbers. However, as you can tell, there are 3 breaks in this graph. Obviously, it's not continuous on all real numbers. Now, again, basically, all you really need to remember is when you write the interval notation for the continuity of the function, you're going to go from negative infinity to negative 5, put a square bracket because of the filled-in dot, and then union. Then you'll have a round parentheses with negative 5. all the way to -1, round parentheses, union, square bracket, -1, 2, square bracket, 3, union, round parentheses, 3 to infinity. Okay? As you can see, the function is not continuous at those 3 x values, but it is continuous on this interval. Okay? My directions will say write the largest interval or union of intervals on which the function is continuous. Because one could say, for example, this function is continuous everywhere from 4 to infinity. That's true, but that's not the largest interval on which it is continuous.
And that's the end of video 1.4D, part 1.